Good morning, class, and welcome to another lecture in sustainable energy technology. So our 12th week is coming to an end and we are coming to the end of our lectures today. So today we will complete most of the syllabus that we can cover in this class, and we will have further maybe a review session eventually, but this is the final lecture of our class today. So till now we were discussing different technologies of CO2 capture, and we went over technologies including sorbent based absorption of CO2 and separation of CO2 using a set of semi-permeable membranes. The last technology that we will look at is the capture of CO2 using cryogenic distillation. The basic idea here is we are going to pressurize, cool and hence liquefy CO2 and separate it through the method of condensation, primarily distillation in this case, from the other CCS components of flue gas like nitrogen, oxygen, etc. So here we initially dry the flue gas, so remove all the steam, and we have initially a flue gas which contains 15% CO2, say 82% nitrogen, 3% oxygen. Okay, there may be some other pollutants that are already removed through certain pollution removal processes like SOx, NOx, etc. And we get a stream at 1 bar 300 Kelvin of dried and cooled flue gas containing 15% CO2, 82% nitrogen and rest oxygen. This dried and cooled flue gas is subjected to multi-stage cooling and compression cycles. So we are going to serially cool and compress this CO2 using a set of cryo refrigerators. It's called cryo refrigerators because they are cooling at very low temperatures, and compressors till the gas reaches around 220 Kelvin temperature and 40 bar pressure. So we are increasing the pressure from 1 bar to 40 bar and decreasing the temperature from 300 kelvins to 220 kelvins. So here you can see you have a cryo refrigeration unit that is for one example here, that is decreasing the CO2 temperature of the flue gas from 250 kelvins to 200 kelvins. Then we are compressing it from 1 bar to 8 bar. Okay, here we have a kind of a cooling regeneration system. We will discuss this because eventually we are cooling both the CO2 and the other gases like nitrogen, oxygen. So eventually that gaseous nitrogen, oxygen which is left is also at a very low temperature. So that gas mixture can also be used to cool the original flue gas initially through a regenerative cooling approach. Okay, so this is what is done here. So initially the output gaseous flue gas at a low temperature is being used to cool the initial flue gas from 300 kelvins to 250 kelvins. Then we are using a cryo refrigerator to cool it further from 250 to 200 kelvins, then compressing it in the first step to 8 bars. This compression is again going to increase the temperature back to 256 kelvins because compression, for those again who are aware of thermodynamics, also causes the gas to heat up. Okay, so again we are cooling this back using a cryo refrigerator back to 200 kelvins and again compressing it from 8 bars to 40 bars at 256 kelvins. So that is why we need a series of cooling and compression cycles, because every compression process is increasing the temperature and the cooling process is decreasing the temperature back down. And the final cryo refrigerator cools this gas at 256 kelvins and 40 bars to the final temperature of 220 kelvins at 40 bars. Okay. Now why is this important? Because if you see the thermodynamic diagram we discussed here, so 40 bars is basically 4 megapascals. So this is 1 megapascals, this is 10 megapascals, so 4 megapascals is somewhere around here. So we are now in the liquid zone and 220 kelvins is somewhere around here. So here now we are in a zone where the CO2 is going to get, can be liquefied. Okay, so we are basically operating now at a temperature and pressure range where the CO2 becomes a saturated gas. It is entering a point where the CO2 portion has become saturated vapor, so that further cooling will start to condense it. Okay. So this is what is important here, that the final temperature and pressure is such that it has become a saturated vapor, so that further cooling is going to condense it to create liquid CO2. And this is being done in the final cooling reactor system. So now this flue gas enters a gas liquid separator. So this reactor is called a gas liquid separator, where further cooling causes the condensation of CO2 into liquid. Okay. So what is being said is this flue gas composition with 220 kelvins and 40 bar pressure, at this stage CO2, which is 15 mole % of it, becomes a saturated vapor. Alright. So this final temperature will depend also on the fraction of CO2 that is present in the flue gas also. It may change depending on the fractional difference. That is not important. We want the final pressure and temperature to be such that it becomes saturated vapor. Then it goes into your gas liquid separator unit, where further cooling causes the condensation of CO2 into liquid, which is collected from the bottom. So this is the liquid CO2 that is condensing in this gas liquid separator, and this is being collected at this 220 kelvins 40 bar pressure. Okay. And the rest of the cold flue gas, now containing only nitrogen and oxygen, which remains in the gaseous stage, is collected from the top and which is used to do the initial cooling of the original flue gas here, and then moving back out. Okay. The liquid CO2, after it is being collected, is pumped to 70 bar pressure, at which point it can stay in liquid state up to 25 degrees centigrade. Okay. So this is also important because it will help in the storage of this liquefied CO2. So remember, the critical point of CO2 is around 31 degrees centigrade. So if you increase the pressure to around 70 bars, then that CO2 can then be stored at or near room temperature of 25 degrees centigrade. Okay. So very high purity liquefied CO2 is obtained out of this, but it is an expensive and energy intensive process. Alright. So this entire cooling using cryo-refrigerator and all of this requires energy. Compression requires energy. So it is an expensive and energy intensive process to separate the CO2 this way. So among the three processes discussed, this is the most expensive process. But something to note here is you are getting highly compressed liquefied CO2 out of this, which is ready for transportation. Okay. In the previous cases, we are not getting, you are getting gaseous CO2, which have to be compressed or stored in some other technology that is also going to take energy. So while this is more energy intensive, if you think of only as a CO2 separation unit, it may actually be competitive if you think of this as a combined technology which both captures and generates a easily storable CO2 system. Okay. So that is one of the advantages of cryogenic distillation. Yes, it is expensive, but you are getting high purity CO2 in an easily storable method. Okay, liquefied compressed CO2. Okay. Now, so we have seen the various ways of CO2 capture. Now the next part that we will discuss is how to transport this CO2 to the point where it is going to be stored. Okay. So there are several ways to do this. First is, as we discussed, refrigerated liquid, or the second part is supercritical fluid. So this is what is we discussed here, that we can pump this to 70 bar pressure and then store it at 25 degree centigrade. So this is your supercritical fluid state, 70 bars, 25 degrees centigrade, and at this point the density of CO2 becomes 743 kgs per meter cube. So 1 meter cube of this supercritical fluid weighs 743 kgs. So it is reasonably dense and requires less volume. Okay, we will compare this with other types of storage systems as well, and it can be stored in cylinders or transported through high pressure pipelines. So that is one method. Another method is you are refrigerating this liquid at a lower pressure. So now this is a liquid CO2 which is being stored at a moderate pressure of 20 bars, but now you have to refrigerate this at minus 40 degrees centigrade. Okay. Now usually liquid is more dense than supercritical fluid, so you are increasing the density of CO2, so the volumetric storage efficiency increases, the gravimetric storage efficiency increases. You are able to store more CO2 per meter cube of space you are using to keep this, about 1030 kgs per meter cube. Remember, density of water is 1000 kg per meter cube, so you can compare with that. Okay, but this has to be stored in insulated pressurized tanks. So not only you have to do it pressurized, but it has to be well insulated. Okay, and you cannot refrigerate indefinitely. You have to refrigerate through the entire transportation system. So the cost is somewhat higher. Okay. Another good option, if you are going for refrigeration, go all the way and store it as dry ice. Now you don't have to compress it at all, so you don't have to pressurize. You are basically cooling it to minus 78 degrees centigrade at 1 bar to produce CO2 ice, which is even denser because it's solid now. So you are again increasing the gravimetric storage efficiency. The mass of CO2 you are storing per meter cube of space you are looking at, and this is the highest gravimetric storage efficiency. 1500 kg of CO2 can be stored per meter cube of space used, but you need insulated containers. Okay, so well insulated containers, because the temperature gradient is even higher compared to the ambient. So you have to store it in insulated containers, and you have to have the cost of cooling it to minus 78 degrees centigrade as well. You have to think about that. Okay, so these are both either cooling or compression, or a mixture of cooling and compression. Okay. Now the next is you are actually reacting the CO2 with different types of ammonia. You can store it either as urea, so NH2 hold to CO. So you convert CO2 to urea using nitrogen or ammonia. So this can be, so we have discussed urea as a way to store ammonia before, as a way of storing hydrogen, but you can also think of it as a way of storing CO2. So this is kind of a good integration of two technologies, hydrogen storage as well as CO2 storage in a single solid medium called urea, okay, which contains NH2 hold to CO2, and it can be stored as at standard temperature and pressure. Urea is non-toxic, very well known fertilizer. The method is well developed already, and the densities are quite reasonable, around 952 kgs of CO2 per meter cube. So the density of urea is close to, so this is not the density of urea, how much CO2 is present per meter cube of this urea, that is what is being looked into. Okay, because that we are thinking of this as a way of storing CO2. Okay, so this is important because you are both storing hydrogen and CO2. So there is a way to integrate these two technologies to create this kind of a urea based storage system, which you can use later to both generate hydrogen at one end for your hydrogen based energy storage cycle, as well as using that as storing CO2 as well, up to the point where you are going to finally sequester the CO2. And storage facility, you are tanks of around 50 meter cube, nothing special is needed, no temperature and pressure, but you will require a large quantities of ammonia. So again, if you are going for a hydrogen based ecosystem, this may become viable. Similarly, you can use ammonium bicarbonate. This is richer in hydrogen and less rich in carbon, ammonium bicarbonate. The density of CO2 is 883 CO2 per meter cube. Okay. This has to be tightly insulated because at temperatures less than 227 degrees centigrade. So there is some issues with ammonium bicarbonate not being stable above 27 degrees centigrade. So this is another option you can use. Okay. So those are the various things. Clearly dry ice is the most efficient. After that, refrigerated liquid. Supercritical fluid you can also use, or you can use urea or ammonium bicarbonate, which has lower requirements on storage facilities. Okay. Next, we finally go to CO2 sequestration options. So the most commonly used method of CO2 sequestration is it is used as a fluid for enhanced oil recovery from aging oil wells. Okay, so this is why the supercritical fluid concept is very useful, because in enhanced oil recovery units you need CO2 as a supercritical fluid. So let me explain what is happening. Captured CO2 is converted into supercritical fluid and injected into older and partially depleted oil wells. Okay. The supercritical CO2 mixes with the oil phase in the reservoir, that is deep underground. You are injecting the pressurized supercritical CO2. Okay. It is mixing with the oil phase in the reservoir, decreasing its viscosity. So the remaining oil, it is not coming out because it's highly viscous. Okay. So what is happening? The supercritical CO2, when it's injected, decreases the viscosity of this oil as it mixes with it, and allows this oil to flow out of the rock pores and into the wellhead where it can be collected. Okay. Part of the CO2, so a mixture of oil and CO2 is coming out because the mixture is basically coming out. Okay. Part of the CO2, not all of it, is sequestered inside the reservoir, leading to CO2 sequestration as well as enhanced recovery of crudes and natural gas. Okay, so the CO2 is coming down, mixing with the oil in the pores of the reservoir, decreasing the viscosity and helping a mixture of oil and CO2 to come up. CO2 is getting separated out because it's a gas at low pressures, and the rest of the oil is being used to increase the production of oil from this aging oil well. Okay. So it is helping in the enhanced recovery of crude and natural gas, and part of the CO2 remains in the reservoir, so it is helping in sequestering the CO2 as well. Okay. Most of the current CO2 sequestration systems in operation is this CCS EOR systems, carbon capture and storage enhanced oil recovery systems, as they are more economically attractive. Clearly you are getting some useful product out of this, you are getting more barrels of oil. So that is partially offsetting the cost of the investment required to compress the CO2, transfer it to the wellhead and injecting that CO2. Okay, because all of that increases the cost. So the cost is balanced by the profit you are getting from selling the additional oil or gas that you are getting out of it. Okay. So most current CO2 sequestration systems are these CCS EOR systems. Examples include, there are several. Weyburn Meadow project in Canada, which is continuing to run, but it was actually monitored between 2000 to 2012, and it was able to sequester around 20 metric tons of CO2 and was able to recover 220 million barrels of extra crude. Okay, so a lot of extra crude was recovered, and a modest amount of CO2, around 20 metric tons of CO2, was sequestered during this period. Okay. Natural gas recovery from unminable coal bed seams can also be done using similar CO2 injection systems. So suppose there are deep coal bed seams from which you cannot extract coal through mining, but this coal bed seams contains natural gas as well. So now you inject supercritical CO2 which displaces this natural gas and it comes out of a wellhead. So you are getting the natural gas out of these coal bed seams, and the CO2 is getting sequestered as well. Okay. So this is kind of a first generation technology. The method is basically a hybrid. You are sequestering CO2, but the main objective is mostly to get more oil or gas out of the system. Okay. But this is important because it helps to mature the technology of this CO2 sequestration. Okay. But if we have to go to the levels of CO2 sequestration that we need, as IPCC tells, to get the main fossil fuel based energy industries to become carbon neutral, you have to look at geological storage options that is not coupled with enhanced oil recovery, and these do come at a cost. Okay, so the cost aspect is primarily a factor. We will so basically you are capturing the CO2, storing the CO2, transporting the CO2, injecting the CO2 in this well, and all of this increases the cost, and this has to be offset from the energy, the profits that the company is making by selling the electricity or selling the oil or the coal, right? So that cost is significant part of the profits that are currently happening, but this is necessary if you are going to have to go towards a carbon neutral method of fossil fuel based energy generation systems. Okay. So the long term viable options include depleted oil and gas reservoirs. So these are oil and gas reservoirs that have been entirely depleted. We have extracted all the oil and gas that can be recovered from it, even with enhanced oil recovery systems. And here we are no longer having an operational oil or gas well from which oil and gas is coming out. But we still have the drilling technologies and everything. We use these regions to pump the CO2 either in supercritical form primarily into these reservoirs and fill up the reservoirs that originally contained this oil and gas with pressurized CO2. So this is kind of a depleted oil reservoir, this is a depleted gas reservoir. You already have these wells in operation that originally extracted the oil and gas out of these systems. Now you are pushing the CO2 into these systems and filling up these reservoirs. Okay. Just as it had oil and gas before, it will continue to have the supercritical CO2 in these regions, and after it has all been filled up, we will close the wellhead to stop this CO2 from coming out. Okay. And the technological cost is less because all the drilling and everything is already there, the pumping methods are already there, so you will have, you do not need as much cost capital investment to do the CO2 sequestration. Okay. And the geological formations are already well studied, and it can store around 675 to 900 gigatons of CO2 based on the current existing empty oil and gas reservoirs. Okay. So that's one. And the next step in the CO2 sequestration stage, from enhanced oil reserve recovery to now using it just to store CO2, these oil and gas reservoir systems. The next part is deep saline aquifers. These are basically porous rocks filled with saline water or brine at high pressures. Okay. So this is the most feasible and provides the largest potential volume of CO2 storage option. Okay. Located at depths below 1 kilometer in sedimentary basins and can store large quantities of CO2 which can mix with the saline brine that is present in these reserves. So this contains a lot of saline brine, and if you inject supercritical CO2 into this, then the CO2 dissolves in this pressurized saline brine and stays there. Okay. Typically high permeability carbonate rocks reservoirs with an impermeable shell cap rock. So this is kind of your salt caverns. You are injecting CO2 in these salt caverns and salt beds, and over here is the cap rock, which is made up of impermeable shale, another type of rock. So this is preventing this saline brine mixed CO2 from coming up again. Okay. Here also a similar kind of a saline aquifer is shown. These are salt caverns. This is a saline aquifer. You inject CO2 in these aquifers also, and it gets trapped here. Okay. Storage potential is large. 1000 to 100,000 gigatons per CO2 can be stored here. Okay. But of course, the drilling technology and all of this has to be done for this reservoir, because we have not used these systems before. We have to look at these rocks, drill these rocks, establish the drilling technology. So it is capital intensive, but this is the long term option for CO2 storage going into the next next 10 to 15 years, after next 10 to 15 years. Okay. Another emerging technology that is in a early stage is injection of CO2 into basaltic rocks. So basaltic rocks are basically volcanic or ocean based rocks, and you are injecting CO2 into the basaltic rocks itself along with water. So you mix CO2 with water at reasonably low pressures. Okay, CO2 water can dissolve a lot of CO2, and that CO2 water mixture you are injecting at reasonably low pressure. So you don't have to go to supercritical or compressed CO2. Okay, and the CO2 basically reacts with the basaltic rocks and get converted into solid state carbonaceous material. So solid carbon containing minerals are being produced. So there is no concern of whether the CO2 will escape or whether that fluid will eventually escape, because it is being converted into solid minerals by reacting with the basaltic rocks there. Okay, so this has high potential, but technology is still not very mature, and it's a very safe kind of a system as well. So these are some of the ways. Now, one of the major challenges is you need continuous tracking, verification and monitoring of CO2 during and after injection. Okay, you need to check if the CO2 is escaping, you need to check if there are seismic risks or anything like that throughout this process. So those aspects need to be very carefully looked at. Okay, there are possibilities of CO2 leakage if the reservoir is not properly analyzed. There are possibilities of seismic activities, etc. It can CO2 can react with groundwater and make the groundwater acidic, increasing the pH of the groundwater. That concern is there. So those risks has to be considered. Potential risk of injection induced seismicity, as we discussed. Estimating potential rise and eventual leakage of a CO2 plume. So whether it is if the CO2 is going to rise and then eventually leak out. Large capital costs are there, especially for these types of systems where there is no drilling technology yet that has been developed, and there are public acceptance that the place where it is happening, will they accept it? Okay, so it may have to be done far away from human habitation, and ethical responsibility. Who will take care that this CO2, this place remains safe for the next 100, 200, 300 years? Who is responsible for keeping the storage, looking at the geology, seeing if there are risks and mitigating these risks over long term? Because there is no actual profit incentive, right? You are just storing it, and somebody has to be responsible for it without having any profit. So how does that work out? So those concerns have to be tackled to make it possible for this technology to develop and mature to a large enough level for this to happen. Potential is there, we have to manage it correctly. So this is the current state of CCS technologies. So this is kind of how much carbon dioxide is being sequestered in terms of metric tons per year, MTPA, metric tons per annum. Okay, the largest are around 8, the smallest are around 1. Okay, and the operational ones are green. Things that are being executed currently are blue. The places that are being evaluated, defined or identified, so early stages are this purple or orange and red. Okay, so most of the established technologies are in US currently. As you can see, large CCS systems do exist associated with enhanced oil recovery mostly. Some small scale systems exist in Europe. There is one interesting offshore system here in the North Atlantic Ocean and off the coast of Brazil. In the developed countries, there is nothing in India. There is a set of early stage projects that are happening in Australia, China and offshore Korea. Okay, but this has to grow very rapidly for it to take up, okay, in the future. So these are all the CO2 capture capacity in million tons per annum. What is the situation, operation, what is operational in different continents, and what in the earlier evaluation stages. Okay. This is the current state of CCS technologies. This is entire thing: capture, transport, storage and utilization. Okay, these are well developed commercial technologies. For example, post combustion amines, so conversion into amines. Pre-combustion natural gas processing, these are different types of capture processing, amine synthesis based systems. Transport, onshore and offshore pipelines, transport ships, saline formation and CO2 based enhanced oil recovery. These are well developed technologies right now. Demonstration stage, you have the semi-permeable membrane based technologies for capture, post combustion adsorption technologies, bioenergy based CCS technologies, direct air capture of CO2. These are all demonstration levels. These are depleted oil and gas fields. So we are currently demonstrating the CCS technologies in depleted oil and gas fields. Then CO2 based enhanced gas recovery from coal beds, etc. This is also in the demonstration stage. The direct air capture is an emerging technology. We are extracting CO2 directly from the atmosphere and then capturing it. Okay, so this is kind of a technology that will be useful if there is if the CO2 emissions increase beyond a certain level, so it becomes too dangerous. So this can at scale help to mitigate that. Okay. Then in the pilot stage, there are certain polymeric membranes that are used in power plant technologies that are still in the pilot plant stage. There are other types of chemical looping combustion technologies, calcium carbonate looping. These are in the pilot stage for the CO2 capture systems. CO2 utilization is in pilot stage. How to utilize the CO2 in more different ways other than that we discussed previously. Then there are other types of membranes, post-combustion capture technologies which are at lab scale or low TRL level. Mineral-based storage, as we discussed in the granite stage, is a low technology readiness level. So TRL is technology readiness level. This is most mature. This is least mature. Okay, so commercial stage, demonstration in commercial, in large scale, pilot scale, lab scale, and these are conceptual stages. Okay. So several capture technologies are well developed. Some storage, most of the transport technologies are well developed. There is a lot of storage technologies that are developed, but there are cost concerns still there in those things, as we discussed. And there are other types of emerging storage and capture technologies that are coming up from the various, there is a lot of research happening in all aspects of capture, storage, conversion and utilization. Okay. Capture, storage, sequestration and utilization. Some are well developed, some are still in the lab scale. Okay. So this kind of gives a snapshot of that. All right. So with this, we kind of come to the end of our discussions on sustainable energy technologies. We were unable to complete the life cycle analysis because of the shortness of time, but I hope that the entire course was pretty comprehensive and gave you a overall 360-degree view of all the technologies that are necessary for our transition from a fossil fuel based energy economy to a carbon neutral and renewable energy economy that is more sustainable. We discussed a set of renewable energy technologies. We discussed a set of storage technologies essential for creating a grid that can work with high levels of renewable energy technologies. We looked at hydrogen economy, which kind of can decarbonize large segments of hard to abate sectors. We looked at CO2 capture and storage technologies that can help make fossil fuel based energy industries less CO2 intensive. And we looked at a broad feasibility of different technologies, where they are at the moment, what are the market potentials, how they are relevant in their different regions, like developed countries, developing countries, etc. And this can help you to kickstart your deeper dives in any of these technology streams while keeping the entire global ecosystem of these energy systems in mind. Okay. So if you are looking at future work in any of these in terms of research or professional level, this course probably helped you, gave you an introductory understanding of the technology and the market, and showed you where it is and where we need to go in the future. Okay. So hope the course has been enlightening for both the students and the professionals who have been taking this course, and we will have the final exams and everything after the courses are over. We had review lectures as well, some review tutorials and tutorial problems as well. So best of luck for your final assessment, and hope you continue your exploration and study of these technologies in the future and make it your successful professional choice. So with that, I am closing this the theoretical lectures for this course, and thank you for being with this journey with me, and best of luck for your future. All the best. Thank you.